So let's get started. So hello everyone. I am Himanshu Mishra and I am the PhD research scholar in the Department of Applied Mechanics. And this week I am going to cover the topics from the flow over the flat surface and the heat transfer due to such flows. So we know that in such flows there will be hydrodynamic and thermal boundary layer which will be developing, and I will be solving question related to them to find out the local or the average heat transfer coefficient rate throughout these flows, and then to find out the heat transfer rate in these flows. So let's begin with the first question here, which is a true false type of a first question. So here we identify the true statement or whether the statement is true or false. So the first question says that so the first statement is the conduction and convection are similar in both mechanisms. Uh, Record that the presence of a material medium, but they are different in that convection requires a presence of fluid motion. Okay, and the second statement is the heat transfer through a solid is always by conduction. Since the molecule, so yeah, hello Abhishek. So can you hear me? Is my voice is audible to you? Okay. So the heat transfer to a solid is always by conduction. Since the molecules of a solid remain at a relatively fixed position, heat transfer to a liquid or gas, however, is by pure convection only. And the magnitude of heat transfer does not depend on the rate of bulk of fluid. So here we can see that the second statement is not the correct statement because it says that the heat transfer in the gas or liquid occurred due to the pure convection only, which is not true actually. So let's say I have a fluid in a beaker or in a tub or a glass or something. So this is my fluid. So in this case, since the fluid is in stationary position and there is no bulk motion of the fluid inside this jar or the glass, the heat transfer will be here will be purely due to the conduction. So there will be heat conduction, which is the most significant mode of the heat transfer in this system. Now, when I started, let's say I have a spoon and I started revolving this liquid, and I generated a vortex motion inside the liquid. When I generate the vortex motion inside this liquid, then there is a bulk movement of this fluid parcel inside this jar, and then we can conclude that the depending on the velocity and other physical parameter, the heat transfer then occur due to the conduction as well as the convection. So here the second statement is not correct. Only the first statement is correct. So the option is B. So let's move to the different question. So the second question is again the true or false question. We need to identify the true correct option between these two. So hello Prabhanjan, can you able to hear me? Hello, can you able to hear me? Am I audible? Hello. Hello, Prabhanjan, can you able to hear me? Okay, nevertheless. So let's move to the. Okay, thanks. So I was discussing the first question where it is a true or false kind of a question. So in the first question, so we need to identify here the correct statement. So the two statements are, one of the statement is the conduction and convection are similar in both mechanism requires the presence of material medium, but they are different in that convection requires presence of fluid motion. And similarly, the second statement is the heat transfer in a solid occurs due to the conduction, and the heat transfer in the liquid and gas always occur by the pure convection. So in this, we need to identify the correct statement. So maybe you can see from the diagram or the rough sketch that I have made. So just to recap, the heat transfer in the liquid and gas can be occurred due to the conduction. For example, here in the jar, I have a fluid in the jar or the glass, and there is no bulk motion inside this container, and therefore the significant mode in which the heat transfer take place is due to the conduction, not the convection. But if I have a spoon, let's say, and I create the vortex rolling motion inside this container, just revolving the spoon and creating the vortex, there will be the bulk motion of the fluid parcel, and then the heat transfer will takes by the convection also, along with the conduction. So here the second statement is not correct because it says that the heat transfer will always be occurred due to the pure convection in the liquid, but it is not true. It depends on the bulk motion of the fluid. So let's move to the second question. So the first statement says that for the case of fluid flow over the flat plate, the region of the flow above the plate bounded by delta in which the effect of viscous shearing caused by the fluid viscosity are felt is called the velocity boundary layer. The boundary layer thickness L is typically defined as the distance phi from the surface at which u is 0.99 v. V is the free stream velocity. So the statement says that I have a flat plate which is stationary and there is a flow incoming. Now as this flow which has the velocity v move move past this flat surface, it creates the boundary layer, some boundary layer here, and let's say this distance is my delta, and the velocity here is 0.99 v, and this is inside this region. There will be the viscous effect which will be felt by this flow, and this distance delta is known as the boundary layer thickness. So this is the correct option. So it's a basic concept in the boundary layer theory. When any flow pass the flat surface, it creates the boundary layer due to the shearing action that take place at the wall of this flat plate. And due to the shearing action, there will be some shear generated, and there will be some shear stress, and therefore it create a boundary layer at the top of the flat plate. And as we move away from the flat plate, we can see that the velocity keep increases, and at one region, the velocity will become approximately to the free stream velocity, and that region will be used to measure the boundary layer thickness from the wall. So the first statement is correct. There is no issue in the first statement. The second statement says that the flow region over the surface in which the temperature variation in the direction normal to the surface is significant is the thermal boundary layer. The thickness of thermal boundary layer del T at any location along the surface is defined as the distance from the surface. So the second statement is also correct. It says something about the thermal boundary layer. So as the fluid is heated and it is flowing past the surface, there will be two boundary layers. First is the hydrodynamic boundary layer, which I have shown. This is my hydrodynamic boundary layer which will be developed due to the motion of the fluid which is sheared over the flat plate surface. And since there is some fluid is at some certain temperature, there will be temperature gradient also, like the velocity gradient. So again, I have a flat plate. And let's say the wall is at temperature Ts, and the flow which is coming from the left is having the temperature T infinity. Now since Ts is not equal to T infinity, the temperature of the flow which is coming from the left is way different than the temperature of the wall. When the flow passed over this surface, this flat surface, there will be the temperature boundary layer because there is a because the both temperature are different to each other. So at the wall, the temperature of this fluid just near to the wall is equal to the temperature of the wall. But as we move along away from the wall, the temperature start decreasing, and at far away from the wall, it attains the temperature of the fluid. So this is a rough diagram of this temperature gradient. So here I have a temperature Ts, and it is start decreasing, and it become the at the thermal boundary layer, the temperature will become the difference between the temperature of the fluid and the solid surface. So again, this my second statement is also correct, which says something about the thermal boundary layer. So overall, my both first and second statement are the correct option. So any doubt in this second and the first question we have? Any doubt? So let's move to the third question. So in the third question, a thin flat plate that is 0.2 meter by 0.2 on the side is oriented parallel to the atmospheric air stream having a velocity of 40 meter per second. The air is at a temperature of 20 degrees Celsius while the plate is maintained at 120 degrees Celsius. The air flow over the top and bottom surface of the plate in measurement of the drag reveals the value of 0.075 Newton. Okay, what is the rate of heat transfer from both sides of the plate to the air? So we have a plate here. Let's say this is my plate, and the question says that there is an incoming flow from the left hand side, and that this dimension is 0.2 meter by 0.2 meter, and the temperature of my plate is 120 degrees Celsius, whereas the temperature of the flow which is coming from the left is 20 degrees Celsius, and we have given the velocity as 40 meter per second. Now we have given the drag force 0.075 Newton when the flow is there over the flat surface, and we need to find the heat transfer rate that when there is a flow, what is the heat transfer rate between the plate and the flow on the both side. So since we have given the drag, we can use something called Chilton-Coulomb analogy. So it actually defines the relation between the drag and the Prandtl number and the heat transfer coefficient. So it can be defined as the drag coefficient CF by 2 as So here PR is my Prandtl number, and this is my heat transfer coefficient. CP is my heat capacity, and rho u and U infinity are the density and the velocity, free stream velocity of the fluid. And CF is my drag coefficient. So I can first found CF. Sorry. So to find out the heat transfer, we need a heat transfer coefficient h bar. So we need to find this h bar. So to find this h bar, we need CF, PR, and CP. CP we can find from any book or internet. It is just a property of the fluid, and there here we need to find the this drag coefficient and the Prandtl number. So to find the drag coefficient, I can write as so this is a relation we are aware about from the fluid mechanics course, that if you need to find the drag on the surface, we use this relationship. I use the exact same relationship here, and instead of force, I have written down. Okay, let me write here as so this relation will be this relation is I am using to find out this drag coefficient, and then I will use the Chilton-Colburn analogy to find out the heat transfer coefficient. So let's first find the drag coefficient. So 0.075 Newton is the drag force which is given. This is my density of the fluid. So on solving this, I can write my drag coefficient as 5.76 10 to the minus 4. Now I can use this Chilton-Colburn analogy to find the heat transfer coefficient rate. So from this relation, I can write my heat transfer rate as CF infinity CP by 2. So I will take this Prandtl number left hand side, so it will become minus 2 by 3. So we already have the drag coefficient. We just need to substitute these properties, that's all, to get this heat transfer coefficient rate. And on solving from this from the calculator, we can just write the heat transfer coefficient as 30 watt per meters per Kelvin. Now we have the heat transfer coefficient. We can just use the Newton's rate of Newton's law of cooling to find out the heat transfer rate over the board surface. So we need to find the heat transfer at both surfaces. That means there is a flow here at the top of this plate as well as the bottom of this plate. So we need to find the heat transfer here as well as at the bottom. So we will multiply this expression with 2. So we already found the heat transfer coefficient here, which is 30. And the area is given as 0.2 multiplied by 0.2. And then the heat transfer rate will be on calculating this we will get P41. So this will be my answer for this question. So here the question asks that there is a flat plate of 0.2 meter by 0.2 meter cross section, and there is a flow which is coming from this left hand side, and when the flow passes the flat surface and the flow having a different temperature of 20 degrees Celsius and the plate having the temperature of 120 degrees Celsius, what will be the heat transfer rate between the flow and both sides of the plate? So for this, we have given the drag force, magnitude of the drag force. That is, when there is a flow over the flat surface, it will create some drag, and that drag force we have given 0.07 P75 Newton. So we use the Chilton-Colburn analogy, which actually relates the drag coefficient with the heat transfer coefficient and the Prandtl number. So we first, to calculate the heat transfer coefficient, we first calculate this drag coefficient, which is obtained from the simple formula that you may have seen in the fluid dynamics, this drag force relation. So from this relation, we found CF, and then from Chilton-Colburn analogy, we found the heat transfer coefficient, which come out to be 30. And once we got the heat transfer coefficient, we just need to use the Newton's law of cooling to get the total heat transfer rate. So any question in this? Any doubt in this? Any doubts? Okay, so let's move to the different question. So in this question, there is a steel plates of thickness del 6 mm and length 1 meter on the sides are conveyed from heat transfer process and are concurrently cooled by atmospheric air of velocity u 10 meter per second and temperature 20 degrees Celsius. For an initial plate temperature Ti, what is the rate of heat transfer of the plate? And okay, so there is a plate which are hanging, we can see from diagram, and there is a flow which is coming from this direction. In this question, we need to find the temperature variation with time. So to find the temperature variation, we already given, or we can see the properties of steel plate, like the thermal conductivity of the plate, heat capacity, density of the steel plate. We can get these properties to use into our expression. So the heat transfer rate will be given by the Newton's law of cooling, and the rate of temperature change with respect to time can be given from the energy balance. So to first found the heat transfer rate, we have this will be by heat transfer, because this will be by plate and there is a flow, so it will flow past both left and right side of the plate. So we are multiplying 2 into here, because there is a heat transfer at the left and the right at the same time. So we need to find this heat transfer coefficient in order to use this equation. So for this, let's check whether the flow is in laminar or turbulent condition, because according to that we will use the Nusselt number expression for the flat surface. So this will be my Reynolds number. kinematic viscosity I can get from the properties of this fluid. And this flow, this will come out to be 3.29 10 to the power 5, which means the flow is still laminar. So we can use the laminar Nusselt number expression correlation. So the Nusselt number can be defined in terms of heat transfer like this. So first we find the Nusselt number. We already found the Reynolds number here. So the Nusselt number will be around 336. And from this, we can find the heat transfer coefficient rate. So this will be my heat transfer coefficient. Now I can use this Newton's law of cooling to find out the heat transfer rate. So my heat transfer will be 6780. So this is the first part of the problem where we need to find the heat transfer. So obviously we need the heat transfer coefficient, which we actually find from the Nusselt number correlation, laminar Nusselt number correlation. We first check whether the flow is in laminar or in turbulent state, and according to that we use the correlation to find the heat transfer rate. Now our second objective is to find the rate of change of temperature with time. So for this we need an energy balance. So this will be our energy balance. So let me write a complete statement. So this is my overall energy balance. So there is no generation of heat, so this will be vanished, and there is no incoming of heat. So let's say this is a plate. So we are not providing any heat to this plate. So there is no energy influx. So when there is a flow past the flat, this flat surfaces, the energy is leaking from the plate, and therefore we will have a finite energy out. And there is a we need to find the change of temperature with time. So there will be some finite energy storage into the system in the system. So this can be written as, so energy out will be governed by the Newton's law of cooling. So when there is a flow, the plate will release energy due to the Newton's law of cooling, because there is a convection heat transfer rate between the air and the plate. So this energy out is just a Newton law of cooling we have just saw. And the energy storage can be given as and we need to find this variation of temperature with time. So we just need to substitute these values. These are my properties of the steel, like heat capacity and the density. So this is my variation of temperature with time, and we earlier found the heat transfer rate, which is I guess 6780 watt. So in this question, there is a flow, and there is a steel slabs which are hanging, and we need to find the heat transfer and the rate of change of temperature with time. So to find the heat transfer, we use the Newton's law of cooling. We first found the heat transfer coefficient by using the Nusselt number correlation, and then we to find the temperature variation with time, we just use the energy balance. So let's move to a different question. So in this question, there is a steel strip emerges from the hot roll section of a steel mill at a speed of 20 meter per second and a temperature of 1200 Kelvin. Its length and thickness are 100 meter, and and density and specific heat are given. Counting for the heat transfer from the top bottom surfaces and neglecting the radiation and the strip conduction effect, determine the time rate of change of strip temperature at a distance of 1 meter. Determine the distance from the leading edge at which the minimum cooling rate is achieved. So we have given a strip, and we need to find the similar rate of change of temperature with time here. So for this, from the previous question, we know that to find rate of change of time, we need energy balance from this strip. Like previous question, we can just write system. So this strip will lose the energy by the convection, and the my energy in the system can be given as dt. So here this will be the rate of temperature variation with time. So now here we need to calculate the heat transfer coefficient first. So when we substitute the property and the temperature, we will have we'll get relation in terms of heat transfer coefficient. So we need to find the heat transfer coefficient first. So for this, we need to check whether the flow is in the laminar or in the turbulent regime. So for this, we will calculate the Reynolds number. So here the Reynolds number is less than the critical Reynolds numbers. So we can conclude this that the flow is in a laminar state. So we can use the Nusselt number correlation of laminar flow. So on substituting the value, we can get the heat coefficient as 8.29. So here I calculate the Reynolds number at x equal to 1 meter. This is my 1 meter. So I can find the variation of temperature with time at x equal 1 meter equals 8.29 multiplied by 0.199. So this is a variation of temperature with time at x equals to 1 meter. Now I can find the similar temperature change with time at x equals to 100 of meter. For this, again I will check my Reynolds number at x equals to 100 meter, whether it is a laminar or turbulent. Again I will check the Reynolds number by the same procedure. And I get